So my name is Scott Jordan. I am currently a consultant for this industry. I've spent 40 years on the topic of photonic process automation for manufacturing, test, and assembly of photonic devices. And I have to say, I'm terribly impressed with what 3SAE has accomplished with their new micro robot. This is called the PentaPod. It's a parallel kinematic device with a very unusual patented configuration that results in extreme stiffness, multiple degrees of freedom, about 6 degrees of freedom, long travels, and resolutions down into the tens of nanometers. Now, that's what this is a positioning device, but what the market has been asking for is a micro robot that can perform alignment optimization of photonic devices in manufacturing, test, and assembly. I think this is what the market has been looking for. Let's take a close look. Here you can see the pentapod performing multi-degree of freedom motions. And that's something that you can see in many different vendors' booths with different types of mechanisms. But what's especially clever about this mechanism is the fact that its particular parallel kinematic arrangement and the way it is constructed results in the most stiff and stable assembly on the marketplace. It is literally stiffer than a steel post, and I can prove it. Come over here. Let me move in this direction here. This first demonstration that they have shows a simple fiber coupling. Okay, so you have a source fiber and an aligned fiber, receiving fiber. Now, this belt coupling arrangement here, you've got one mechanism or one fiber, the receiving fiber is mounted on top of the pentapod, and the other is mounted on top of a steel post. The throughput of this fiber is going through an amplifier, an audio amplifier with an actual speaker. So look what happens when I tap. Hear that? Okay, I'm tapping the steel post. You can hear the resonant response of the assembly. Now watch what happens when I tap the platform itself. Not only is it much quieter, meaning there's less deflection, which means it's stiffer, but it also settles much more quickly. And that goes directly to process reproducibility and process speed. So the stiffness of the assembly is not just a number of interest only to engineers. It goes directly to the robustness of your application. If there's external vibration, if there are disturbances, if there are people walking around, this assembly will be impervious to that type of disturbance. So the highest stiffness of any multi-axis stage, it sounds like hype. It isn't. It's something that will greatly benefit photonic manufacturing applications. Let's move over here. This assembly and the way it is constructed. You will notice in some animations that are playing on the screen here, you'll see how it is constructed with 5 linear actuators and a V-shaped workpiece. And the way those actuators are connected to the workpiece, they're preloaded against the V-shaped workpiece using, depending on the model, depending on the platform, magnets or springs. And what that means is you do not need the complicated arrangement of rotational bearings or spherical bearings that are normally used in parallel kinematic mechanisms. Now, let's review those. The spherical bearings are typically used in low-cost parallel kinematic mechanisms. And the reason that they're used in low cost is that they're not very stiff. And we've already talked about stiffness and the benefits of stiffness in process robustness and reproducibility. In this case, you have a very stiff interface between a hardened ball and a sapphire plate. So it's hard to imagine anything that is stiffer than that. Certainly stiffer than the spherical bearings that are used in cheap hexapods and other parallel kinematic mechanisms. The other approach for parallel kinematic mechanisms is to use two offset cardanic joints. In other words, typically angular contact bearings, one for each degree of freedom. So you've got, for the two at the top of the leg, you have two of these angular contact bearings. And then at the other end of the leg, you have two more. So that's 4 per leg times 6 legs. So one of these mechanisms, one of these products will have 24 expensive angular contact bearings that they're preloaded. They need fancy machining, fancy assembly, and the whole resulting product is complex and costly. In this case, oh, by the way, also, you have 24 of these, which means the stiffness is going to be reduced commensurately by the time you add up all of the 6 legs and their 24 rotational bearings. So this is where the stiffness advantage of the PentaPod and its new stablemate, the Octapod, this is where its stiffness benefit comes from. It's very simple. Point contact design of hardened surface against hardened surface is considerably more stiff than anything that can be achieved with 24 bearings or with spherical bearings. So again, this goes directly to the ability of the system to be robust in industrial applications when actual human beings are using it. Okay, there's another thing. I should point out the load capacity. This is a true parallel kinematic mechanism. So you have the load is being supported by all those actuators acting in parallel. There's no indeterminacy, no possibility that the system might rock, for example. So it has a high load capacity. In this case, you have a 2 kilogram load capacity being shown here. This camera is looking directly at the new element of the Octapod. So this gets me directly to the advancement that 3C has introduced here at Photonics West. This mechanism right here is a specialized mechanism for the dithering application, the dithering process that is used for aligning and tracking photonic couplings. This is a new capability. That's what separates the Octapod. It's 2 additional degrees of freedom on top of the 6 degree of freedom PentaPod platform. So here you have a slow motion version of the dither process that is used to drive the gradient search optimization. So it's slowed down so you can see it. So this mechanism is devoted to doing that constant motion. It's not a positioner in its own right. It is intended and specifically limited to performing these small circular motions that are used to generate a photonic error signal that drives the alignment optimization process. So that's what this demonstration is meant to show. So you can see how this addition allows frictionless, essentially infinite lifetime, and very high dynamic motion of this sort. In this case, it's slowed down, but it could go up to tens of hertz, not a problem. Here is where we start getting into really exciting stuff. Multi-channel photonic alignment. So here we have another Octapod with photonic arrays of fibers, single mode fibers, in this case, a linear array with cables coming out. And in this case, we are performing very rapid alignment. I'll have to show you on the screen what the alignment looks like. Let me move over here. And, okay, I'll call up this demonstration here. Let me clear the graph. Okay. So What we're looking at is the output of the coupling of those two fiber arrays. Now, if I move, let me really screw up the alignment here. I'm going to move into two transverse axes and greatly damage the coupling. As you can see, there's just much less coupling than there was before. So now I'm going to perform the grading and search, and you can see that in less time than it takes to describe it, the coupling has been recovered. Now, that is the combination of the pentapod's alignment motion and the additional dither mechanisms generation of the photonic error signal. This is a generic alignment micro-robot for photonic alignment purposes. It's optimized for industry. The pentapod itself is very much a known commodity. It is the heart of what are widely regarded as the world's best fusion splicers. There are many hundreds, maybe thousands of units in the field for years. Their reliability is proven. Greater than 20,000 hour mean time between failure. On the rare occasion that a repair is necessary, it can be performed in the field, in situ. It's about 20 minutes to replace an actuator. And the point is that'll hardly ever be required. Think about some of the advantages here. We talked about the stiffness, the robustness, the fast settling time. You've seen the fast alignment, the multi-degree of freedom capability. Let's talk about cleanliness. No one ever mentions cleanliness, and they need to. This photonics industry is just starting to wake up to the need for cleanliness in what were formerly regarded as back-end processes, such as probing, wafers, assembling devices themselves. Formerly, these were regarded as something you could do in a sandstorm because the wafer is fully patterned. Who cares about particles anymore? Photonic devices definitely care. So the cleanliness of this mechanism, the lack of bearings and exposed motors and cables and things of that sort, make this something that is very suitable for today's photonic production applications, because cleanliness is a big part of that. I haven't even mentioned one of the things I think is the most clever and wonderful of these applications, of this mechanism here. I'm holding the mechanism. I'm also holding the controller. The controller is built into this unit. This unit has a USB interface. This unit has USB plus Ethernet. You want EtherCAT? That's possible as well. This means it can be implemented as part of your fab automation solution. It can be embedded into tools, whether your internal integration team is building its own mechanisms, its own assemblies, its own tooling, or whether you're working with OEMs or integrators, external integrators, to build a custom tool to meet your needs, or whether you're an integrator yourself or a tool maker and you want to be the next KLA or the next Applied Materials, the victor in the battle to be part of the ecosystem of tomorrow's photonics world. Well, here you go. Everything you need, you can hold in your hand, and it works very fast. I could not be more impressed. So here's contact information, and you can call up 3SAE. You can call me as well. I'm happy to help with any implementation needs or any strategizing that you might have in mind. Thank you.